exercise A1 asks us to do. So now we're going to go over to the part B counterpart of this exercise, which is to interpret this output here. Okay. So it says first, consider the OLS estimator. Yeah. So the first column of our table now. Does this PRF help explain the rejection frequencies for TOLS in the table? Okay. So let's perhaps go back to the table. So we're asked to look at first the OLS results. Yeah. So we know in the TGP, beta 1 is 0. So if we're really estimating it consistently, we would expect to see here a very low rejection frequency. So if we're testing at the 5% level, we would like to see in all these cells, in the cells of the table, we want to see really 0.05. Yeah, that's what this table should be. But what we see is that for the OLS, we see an extremely high rejection frequency. But at 400, it always rejects. And the question is, why? What's going on? And the answer to that question, does anybody know the answer? Or want to say the answer? Okay, I'm ready to say the answer. Yeah, OLS is inconsistent because we have an endogeneity problem. Yeah, we've seen that X1 is endogenous, and in last class we've even derived the value of what OLS is estimating. It's estimating this parameter here, which is then minus 0.35. Yeah, and so when we are testing, that the OLS estimate is equal to 0, it's really testing in a circumstance where OLS is estimating this minus 0.35. So if you see us as estimating, as testing beta 1, 0, then this test is horrible. It's doing all the opposite of what we want. It's always rejecting, and it should almost never reject. But if we understand that OLS is really unable to estimate so let's say the causal parameter beta 1, it's just estimating this alpha of this short CF, and the true value is different from 0. Yes, and so this is the power of the test in this TGP. So what we're really seeing is the power of the OLS.
I have a question.
Mm-hmm.
Where does minus 0.35 come from? We manually calculate that value. Yeah.
Yes, that's what we did last week. So
oh yeah.
We obtained this by using the omitted variables formula.
Oh yeah.
So here we would have to insert. We know that short is equal to long plus the effect of omitted times the correlation between the two.
Yeah, yeah.
And in this case, the long effect is 0. The correlation is this 35. And so I don't remember, but so the other effect must be 1. This is how we
okay, yeah.
Yeah, so this is like one very long exercise that's spread over 2 weeks of tutorials.
Yeah, sure. Yeah, I understand. Yeah.
Good. So so this is, the interesting thing here to note perhaps is, so what we interpret. Yes.
Sorry, I still got another question for this. I find that for the TOLS, for the n equal to 100 and n equal to 400, there is slightly different than for the first value, that 0.782. I find that it's the 0.782 and the like the 0.755 for the for n.
Okay. I'll check that. I'm not going to run the simulation now, but it's possible that either I or the teaching assistant changed the random seeds, and this will then makes.
Oh yeah, okay.
Yeah. Yes. Okay, I'll make a note to check that. But yeah, if that's the case, it's probably that's the explanation. So this means that probably everything is a little bit different, or it could be that it depends on which. Because we're really doing this exercise, this experiment twice. Yeah, you can take either the results from when you have rho equal to 0.6 or when you have 0.1.
Yeah.
They will just be different by simulation error. So that's the other possibility.
Oh yeah, it's okay. Yeah.
Good.
Okay.
All right. Thank you. Yeah. So coming back to this question, perhaps the interesting, I guess, the interesting thing for you to learn here is that so we have rejection frequencies, and what they mean or how we interpret them really is a little bit a function of what we're interested in. Yeah. So if we see this as a test for beta 1, then this is the size, and it's a terrible size. If we see it as a test for alpha 1, then this is power, yeah, because this, the null is false, and it's actually a pretty good power. Yeah, so again, whether something is biased or unbiased, and therefore whether the tests are, what they are, they're always a function of what our object of interest is and what we're trying to estimate. And so that's perhaps a good thing to keep in mind. Okay, the next question, so that was about the column with OLS. The next question is about the IV. It says explore the rejection frequencies for the TIV, the table, considering what we've done last week. So here we see that in this circumstance, we get more or less what we want, right? We want 0.05, and we get around 0.05, so this is nice. That's because IV is consistent, so we are estimating beta 1 consistently as 0, and the test works well as it should. When we go to this case, they no longer look so nice. Something which is good is that as we increase the sample size, it goes in the right direction. Yeah, so it seems like it's working. Remember, IV, everything that we know about IV is really asymptotic, so when n is infinitely large. So all these properties are really only guaranteed to hold when n is infinity. Of course, we expect them to hold much sooner, and in this case, when we have a strong instrument, we see that with even 100 observations, we're already fine. When the instrument is weaker, perhaps, then it takes longer. Yeah, and therefore this asymptotic distribution. Yeah, we were saying OLS IV is asymptotically normal. This is obviously not providing a good approximation to how the IV distribution looks here, and this is why we get these poor results. Right? The test is undersized. Any questions about that? If not, let us move forward a little bit. So now let's go back to the A part of the problem sets, and let's do the exercise A2, which is just another exercise about testing, but here just in the context of OLS and with a real data application. So let me share the screen. We're going to do this exercise directly in R. Okay. Good. So we're using some data that has information on how high people are. Let me see if I can load it. Yeah. How tall people are. Yeah. So size. This is an American data set, so I think it's in inches or something. And how much money they make. And there's going to be a question here: what's the association between the two? If there's sort of like a bonus for being tall. This is of course completely descriptive. We don't have a theory for why people who are tall should earn more or less. But it's just an empirical starting point that then one can sort of like try to dig in. As I said, American data sets, so heights in inches. I don't know. To me, that I'm not used to thinking in inches. So what we can do is we take the log. We can also take the log of earnings. Yeah, we don't know from what these numbers are. Yeah, we don't know from, say, it doesn't say here in the data from which year, so we don't know how much. Presumably, if it's American, it's dollars, but we don't know. By taking the log, we circumvent all these problems, and we get a nice interpretation in terms of an elasticity. Yeah, so we see a percent change or a percent difference in heights, and we see a percent difference in earnings. Good. The first 3 questions in this question ask us to run the regression of log earnings on log heights, and then construct a confidence interval, 95% confidence interval, and then do the same. Yeah, so this is a data set where we have both men and women, and so then they ask us to do this separately. So do this regression only using the men in the sample, and do the same regression only using the females in the sample. Let's do that. So here we're transforming the data, yeah, because we have height, we're making log height. Let me run this. Good. And then we are running the regression. Yeah, and so what do we do? Something that I dislike about R is that it's very, it always hides a little bit the number of observations that are being used in estimation, which is, I think, an extremely useful statistic, yeah, to know. Because sometimes when you change your specification, if you have missing values in the variables, the sample composition is going to change. And usually we don't want that. We just want the specification to change, not the sample size. So it's good to keep track of the sample size, but it's a little bit difficult in R. Or it's not difficult, but it doesn't give the sample size as default. So here, yeah, with number of observations, and you put in whatever you call the regression, this is where it's stored. So in this case, you see this is a large sample with 17,870 observations. And what do we see? This is the elasticity. We see if you're 10% higher than if you're 10% taller than me, then you're predicted to have earnings that are 13% higher than my earnings. Yeah, this is what this coefficient here means. And the question though here is to make a confidence interval. And so let me run the code. This is how you do it. I think it's not so interesting. This is one of those exercises where if you do it yourself, it's you gain some insight. Otherwise, it's not really that much to explain. You see, we just pick out the coefficient. This is what we need. Then the standard error, and we are making, to make the confidence interval, we use the coefficient estimate plus, minus, and then the quantile from the t-distribution. That should be around 2, yeah, because we're doing a 95 confidence interval. We have 17,000 observations, so even though we formally take it from the t-distribution, yeah, qt is the quantiles from the t-distribution, we could also take it from the normal distribution. So that would be q norm. Wouldn't make much of a difference because the sample size is so large. We take out the 97.5 fifth quantile, because we're doing this is like a symmetric test, and we use that as a basis for constructing the confidence interval. What's the degrees of freedom? Anybody know what the degrees of freedom would be here, the correct degrees of freedom? It's the sample size. Yeah.
minus 1?
Minus?
N minus 1?
N, almost. So it's N is a good starting point, minus is also good, but in this case, minus minus 2 because it's just minus the number of parameters, estimated parameters.
Oh, yeah.
Both these are going to have, regardless whether we test on with this one or this one, n minus 2 for both. Or if we were controlling for more variables, n minus k. Yeah? All right. Not that it would make a difference here, as I said. We could write Q norm, and then we would directly get 1.96. Good. And with this, yeah, here is the formula. The lower bound minus, the upper bound plus, and we get this, this confidence interval. Next thing is to do the same for subsamples, the subsamples of women. This is what we do here. Let me just show you the results. Okay. I should have asked you first what you think, whether you know it's going to be larger or smaller than the whole sample. So here you see that for the female sample here, the association between height and earnings is weaker than overall. Yes, it's almost 1. It's essentially 1, right? So 1% higher, 1% more income. And now we can make the same confidence interval. Yeah, and we see that it's not so precisely estimated, yeah, especially consider that we have here 17,000. Well, how many? Here we have almost 10,000 is our sample size, so it's not so precisely estimated. You see the elasticity with 95% confidence is somewhere between 0.7 and 1.3. So now I can ask you, what's the outcome going to be for men when we do this for men? It's going to be a number that's larger or smaller than this one? No takers, no answers.
Larger.
Larger, yeah, of course. Of course, because we've done the whole sample. You can imagine the whole sample is like an average of men and women. So we have seen the sample was, I don't know, 1.3 or something, and women was 1, so it must be that men must be higher, so the average is higher. Sample size for men is a bit lower than, so we have about 8,000 men for the 10,000 women, and you see the elasticity is much larger for men. Yeah? So 1% higher, almost 2.5% more income. And we can do the same confidence interval as before. All right. So the last thing that we're asked in this question is to test whether the coefficient for men and the coefficient for women are different from each other. And this is a very common type of thing that we want to know. In this case, they're very far apart. So it's almost like a foregone conclusion that they're statistically significantly different from each other. But sometimes, you know, you divide your sample in two, estimate the same thing with these two groups, get slightly different estimates, and you want to know, is this just by chance or are they statistically significantly different? So how can we do this? It turns out that when you have a cross-section, like here, yeah, so random sampling, a cross-section, and you divide your data so that there's no overlaps, such as when you say, you know, these are the men, these are the women. In that case, we can test this just from the information that we have in these two outputs here. Well, this is the same thing in this output from this one. Yeah, what we need is just the two coefficients, and we're going to make the difference, of course, between them. Take the difference, and so we're going to do this as a t-test. Yeah, so this is here. You see, this is our difference. And next, what we need is the variance of this difference, or to be more precise, the standard error of the difference. So usually, the variance of the difference is the sum of the variances minus 2 times the covariance. Yeah? But here, because we have independent samples, there's no overlaps between them, and because it's a random sample, one observation is independent from the other. These are independent samples. So the coefficients are also going to be independent from each other. And this means that the difference of the variance is just the sum of the variances. And here we have the variances, that's the standard error squared. So here we're making the sum of the variances. And because what we really need is the standard error, we're then taking the square root of it. Yeah, that's what we're doing. And then we are making our t-statistic, the difference divided by the standard error, and the rest is really the same. So when we do that, we get this p-value. You see this p-value is tiny, 0 point, and then 8 zeros, and then 1, 1, 4, blah, blah, blah. So we reject that they are the same at all conventional levels, statistical significance levels. Okay. Then there's one last question here, which is to say, okay, that was easy, but actually there's an even easier way of testing this, in which we just do it all in one regression by estimating a regression with an interaction. Yeah. So we're asked to estimate the regression of L heights, sorry, of log earnings on sex, height, and the interaction between the two. Yeah. So let's do that. Here we go. So you see how easy it was to build interactions, yeah? Just perhaps there's an assignment where perhaps you're asked about to do interactions and so forth. So here we're just specifying log heights times sex, and it's automatically not just including log heights times sex, but also heights and sex itself. Yeah, so we have the whole thing. And what do we get here? We get 4 values. Here we have 4 parameters, and we know that so sex is 0. What is 0? 0 is female, 1 is male. By the way, this is a very bad way of coding variables. So take this as an example of how not to code a variable. You should not code a binary variable sex, because we don't know, what the labels. It's not intuitive what the labels mean. So if you're coding sex in such a way that 1 means male, then it's better to call that variable male. Yeah? Or if you have coded 1 equal 1, it means that the individual I is a woman, and 0 men, then call that variable female or something like this. Because sex just doesn't tell us anything. Okay, here it is the case that male is coded as 1. So this here is the interaction between the two. This is just the variable sex, and this is the variable height. So when sex is 0, yeah, that's the case when we are considering what is this CEF for women, then these 2 terms here disappear, yeah, because these variables are 0. So 0 times these betas is 0, and so we're left with this intercept and this height coefficient. And if you look at them, they're exactly the same than what we have estimated. Yeah, 629, 101. That's exactly these numbers here. And when sex is equal to 1, then we have these 2 variables, the same 2 variables, plus these terms on top. Yeah, so the intercept now is this plus this. And if you this difference, yes, 629 minus 0 minus 6.07, you get exactly this number here. And for the coefficient on height plus the coefficient on height times male, but male is 1. Yeah, so if you add these 2, 1 and 1.4, you get the 2.4 that we had before. But now, so these are really the differences between men and women. And so this is the difference in the effect of height. And we can directly text. Yeah, we have here this difference. We have a standard error for the difference, and here we have the corresponding test. So you see it's exactly the same what we did here. If you look at these values here, they're numerically identical here. So this is a much better way, a regression-based way of doing that test. Okay, that's exercise A2. Any questions here?
Why we don't just like in this regression we just clarify that the random regression of learning on the height plus the sex plus the multiplication of these two.
Your question is why don't we just do the last bit A? Why have we bothered doing D?
No, I mean this regression.
Yeah.
I think it's fine that we just we just run the regression of learning on the height plus sex plus the multiplication of these two rather than like in here this form. I think this form is not make sense.
This is just that form is R short form. Yeah, so R will evaluate these variables.
Yes.
It will say, this is a continuous numeric variable, it's a factor variable, and then it will automatically do the whole thing.
Oh yeah, so it will automatically produce.
You can also do it by hand, sort of like make this interaction before, like here, write, so call it interaction, interact, height, sex, right? And then sort of like by hand define this variable and then put the 3. That's also fine, of course. Yeah, you can also do it.
Yeah. Okay.
This is just sort of like quicker in a way. And if you did this plus sex, then it will just drop sex because it's already like it's not. Obviously, you cannot have these 3 terms plus sex again, right? So it's so if we do this, yeah.
So it's the same.
Yeah, it's okay. It gives the same. It automatically has dropped that. It has even it has spared us the embarrassment. It doesn't even mention that it has dropped anything, right? It just gives us variables. Yeah.
Okay.
Okay. Good. So now let's go back to theory. So this is all for the exercises of part A. Now we